In this video, I am going to discuss the laboratory setup for a computer-controlled wind power system. Here we mainly focused on the main components of a wind power plant. Furthermore, we can study the main factors which influence the generated power in a wind power system. Then determine the relationship between the wind speed and the generated power of the aerogenerator. The IV curve of an aerogenerator for different wind speeds. And determine the relationship between the pitch angle or blade angle and the generated power of the aerogenerator. For this laboratory, we need the following equipment. Computer-controlled wind energy unit or EEEC. DC load module. Data acquisition and control software, and a personal computer to operate the above software. Wind energy is the fastest growing energy technology in the world. It currently makes up a small percentage of our total energy demand, and the rate at which it is growing promises to make it an important part of our energy mix in the future. The term wind energy or wind power describes the process by which the wind is used to generate mechanical power or electricity. Wind turbines convert the kinetic energy in the wind into mechanical power. This mechanical power can be used for specific tasks such as grinding grain, or pumping water, or a generator can convert this mechanical power into electricity. Simply stated, a wind turbine works the opposite of a fan. Instead of using electricity to make wind, like a fan, wind turbines use the wind to make electricity. The wind turns the blades, which spin a shaft, that is connected to a generator and then generates electricity. If we discuss the parts of a wind power system. Rotor, the blades and the hub together are called the rotor. The rotor is bolted to a very strong disc on the big main shaft. Most turbines have either 2 or 3 blades. The length of the blades on the biggest wind turbines can reach up to 39 meters. Nacelle, the nacelle sits atop the tower and contains the gearbox, low and high speed shafts, generator, controller, and brake. The nacelle is nothing but a cover inside which various parts of the wind power system are installed. Gears connect the low-speed shaft to the high-speed shaft and increase the rotational speeds from about 30 to 60 rotations per minute or RPM to about 1000 to 1800 RPM. The rotational speed, required by most generators to produce electricity. Generator, used to convert mechanical energy into electrical energy. Tower, the tower has to carry the nacelle and the rotor. It has to be very tall as the wind is strongest at the top. On the ground, it is not as windy as just 40-70 meters higher up. The stronger the wind, the more energy is in it. That is why the rotor should be as high in the sky as possible to make the wind turbine generate more power. This is the typical wind power system. Here the fan as the wind generator will make the air flow towards the aerogenerator. And it will produce DC power. This generated DC power will be used to charge a battery bank. Then we can supply for the loads using this charged batteries. There are 2 types of loads. AC loads and DC loads. We can connect DC load directly with batteries. There should be a mechanism to transfer DC power into AC power. Therefore, we use an inverter. So that, we can connect AC loads as well. This is the practical setup for our experiment. This is the wind power system. You can see a fan at the rear end. We are not going to use actual wind flow. Instead, turn on a fan to produce airflow. This is the computer-controlled wind energy unit or EEEC. Tunnel to travel air towards the aerogenerator. This is the DC load module. There are 3 positions in 3 DC load conditions. Via this load selector, we can select the appropriate load. At position 1, no load condition. In position 2, 2 DC lamps, and the rheostat can work in parallel or separately. Next, position 3, is the DC motor. These are the aerogenerator configurations, either with 2 blades or 3 blades, or 6 blades. This is the SCADA system. We can monitor real-time values and extra output parameters. Sensors display temperature measurements, airspeed measurements, current measurements, voltage measurements. In addition, channel selection and other plot parameters could be added if needed. The real-time graphic display is also there. 3 parts of a SCADA system called a controlled interface box, data acquisition board, and software packet. This software packet allows computer control data acquisition and data management. On the PC, the EEEC software is installed. There are 3 parts to this experiment. Part A, study the power generated by the aerogenerator with different wind speeds. Part B, determination of IV characteristics of the aerogenerator. And Part C, studies the power generated by the aerogenerator with different blade angles. Let's look at Part A, study the power generated by the aerogenerator with different wind speeds. You can see here the blade angle was changed to 60 degrees. Power changes with air density, the rotor area and the cube of wind speed. In order to study the power as a function of the wind speed, we will try to keep the density and the area of the rotor constant. Under this experiment, fan speed will be varied and, for each fixed speed, every data will be taken such as voltage, current, and rotation speed. We need to make sure that every sensor is correctly connected, and the fan is turned off before starting the practice. Put the selector of the DC module to position 2. As we discussed earlier, at position 2, 2 DC lamps and rheostat can work in parallel or separately. But with the switch, disconnect the load rheostat that is connected in parallel with the lamps. It means, lower the switch position. Then turn on the DC module. After that, turn on the controlled interface box of the SCADA system. Run the EEEC executable file on the personal computer. Make sure that the PC is connected to the main interface via the SCSI cable. Again, software should start by pressing the Start button available at the interface. Set Me selector to before position. And turn on the fan. Set a low fan speed of A1 speed of around 30%, and gradually increase it to full speed. We can see the RPM values, voltage, and current values. Now the fan is at its full speed. We can change the speed of the fan and observe the relevant values. We can refer to it in the results section of this video. We need to get the DC power value from the software. Therefore, using the Calculation tab, we can see the power value. This is how the aerogenerator rotates at its full speed. After taking all the readings, turn off the fan, DC module, and finally the main interface. Now, Part B, Determination of IV characteristics of the aerogenerator. Turn on the DC module and place the DC load selector to position 2. Position 2 means 2 DC lamps and rheostat. It is already in position. We need to place the position of the DC load rheostat at maximum resistance. We can rotate it full leftward. Disconnect the DC lamps which are connected in parallel with the rheostat by lowering the switch. Run the EEEC executable file on your personal computer. Make sure that the PC is connected to the main interface via the SCSI cable. Again, the software should start by pressing the Start button. Available at the interface. Set Me selector to before position. Turn on the fan. Move the controls of A1 to 50% and we can see the corresponding airspeed, output voltage, VDC, and output current, IDC. Approximately decrease the rheostat resistance, R, by 10% and we can see the VDC and IDC values are changed. Rotate the rheostat until the 0% of R is reached. This is the short circuit point of the aerogenerator. Increase the airspeed by setting of A1 to 80% and let's see the same readings again. Now let's move to Part C, study the power generated by the aerogenerator with different blade angles. Here, what we have to refer to is, changing the blade angle and seeing the power generated. Again, turn on the DC module and place the DC load selector in position 2. Position 2 means 2 DC lamps, and rheostat. Disconnect the load rheostat which is connected in parallel with the lamps. This means lower the switch. Run the EEEC executable file on personal computer. Make sure that the PC is connected to the main interface via the SCSI cable. Again, the software should start by pressing the Start button available at the interface. Set Me selector to before. Move the controls of A1 to 60%. These are the IDC and VDC values. Now we have to change the blade angle. It is already at 60-degree pitch angle. Losing this blade screw, we can change the blade angle. This reading is for 90-degree pitch angle. Now we make all blade angles 90 degrees. Tighten the screws. Move the controls of A1 to 60%. The values are 0 since the blade is perpendicular to the wind flow. And this is how the rotor rotates.